Thank you, Luis, for that introduction. Just to make sure, can everyone see the presentation on the screen?
Yes, it's good.
Perfect. Okay. Yeah. So as Luis was mentioning, the motivation for this project came from a problem that we were working on in the industry for a consumer goods company, and it was when working on the industry and these kinds of problems, you notice that there is a very limited set of tools and strategies that people use to optimize, mostly because of the pressure of like getting results really quickly. And so for those projects, we were just using traditional optimizers and considering only demand in a planning horizon, in a limited planning horizon. And then when I was working on this, I noticed that, well, we were doing the same optimization every day. And really what the goal was for the company was to optimize something into the long term. So the motivation to use reinforcement learning for this is to really optimize for that goal in a sequential decision problem over time, rather than just like optimizing for the variables that are in your deterministic space, in the space that you can see right now. So we took that as the base for the thesis project, and this is what came out of it. Where the project is about reinforcement learning and graph neural networks, and that is because, as we're going to see very soon, the problems of distribution and supply chain are naturally graphs, and there is valuable information that could be exploited from that graph structure. And so, yeah, let's dive into it. So as a motivation to understand the kinds of problems that we're working with, consider the most simple case of a company that has a couple of warehouses. Let's call them DCA and DCB. And there is one order that a customer is requesting, which is comprised of two kinds of products that we're going to be calling commodities. So the order is composed of 3 units of the blue commodity and 1 unit of the red commodity. And so the question is, well, given that there's different inventories in each warehouse, what's the optimal way of shipping everything from a single warehouse to the customer? So it turns out that even for such a simple example as this one, since most of the inventory required for that order is on the warehouse DCA, if you choose the wrong warehouse, you have to move 2 more units in total across the system, and that's like like a 30% increase in transportation costs. So this is a good illustration of how like very simple decisions can have a huge impact in supply chains, and obviously supply chains are very high scale operations, so all of those costs really add up to millions in the end. And usually the problems that you're working with are a ton more orders. And as I mentioned, it's a problem that grows over time. Orders keep arriving every day, and you need to consider what your inventory is going to look like in the future, what your order backlog is going to look in the future. And all of those things need to be considered in these kinds of optimization. So why is it a difficult problem? Well, in a nutshell, what we're talking about here, for people that are familiar with operations research, it's a variation of the transportation problem. So we have a network of locations connected with arcs that have certain costs. So for example, here we have an arc going from Miami to Nashville with a $3 per unit cost. And we also have a set of supplies and demands that we need to move from supply locations to demand locations. And the goal is to do this with minimal cost given the network of costs that is here. So this is essentially a linear program, if you're familiar with that. And the thing is that in real life, problems are typically not as simple. So as you add dimensions and complexity to this problem, the computational difficulty also increases. Some of the simplifications that make this unrealistic, well, there's no mention here of the transportation time. We don't know how much it takes, how long it takes for something to arrive from Miami to Nashville. We're assuming that there's just one kind of product on all the supply and demand nodes. And we are completely forgetting about the fact that the orders are arriving each day, and there's no consolidation of the orders, as I illustrated in the previous example. And the optimization cost is just what you can see here, the supplies and demands at this point in time, and not like the long-term cost optimization that could happen. There's also tons of other things that could be added here. The cost could vary across time. There could be capacities based on, for example, the number of trucks you have for each location, that kind of thing. But yeah, for the time being, let's just focus on these. So what we did is we tried to condense some of these characteristics of a distribution network, and we created a new problem that we call the shipping point assignment problem. The goal is that given their customers requesting orders with multiple products every day, try to minimize the transportation costs by rearranging warehouses and the assignments of orders to warehouses. So this is more on the technical side. It's a variant of what's called the multi-commodity minimum cost flows over time. So as I mentioned, this comes from the transportation problem. That's a linear problem, and it's also called a minimum cost flows problem. Then when we add the time dimension and we add the multiple commodity dimension, that goes from being a very easy to solve linear program to actually an NP-hard problem that there's now no real solution for a reasonable amount of time. Some definitions, just that we're clear, when we say warehouse, we mean a facility that is storing the inventory or the supply in the previous example. Customers are the ones that are requesting the orders. Commodity, as I said, is a product, and then cost is the relative monetary value of transporting or storing goods. So I mean relative, because what we're really interested in is, well, what the cost of a transportation between warehouses is obviously much higher than storing inventory on a warehouse. So that's what we really care about. And then an interplant movement, if you see me mention that, is just a movement of units between warehouses to consolidate the inventory. And finally, an illegal movement, more on the technical side as well, is when you decide to ship an order from a warehouse that is not feasible. For example, a warehouse that is thousands of miles away could not feasibly serve a customer that far. So some rules, restrictions, and assumptions that we are making just to have this problem be manageable. The customers are issuing a fixed number of orders every day, and then there's an agent in the reinforcement learning setting that must choose which is the most effective warehouse. So the action space is actually the number of warehouses that you have. And every day new orders appear and the inventories are replenished in a specific fashion. Some restrictions, as I mentioned, all of the composition of an order must be shipped from one warehouse. That we call the order consolidation requirement. We can't miss any delivery, so there's no back orders. And the customers have a subset of valid warehouses, as I mentioned. And if you don't go with one of those, it's an illegal movement. And then assumptions, the inventory replenishment is a random process with a known distribution. We don't mess with the costs. They're always constant, both inventory and transportation. And finally, just to make the optimization problem easier to manage, the supply and demand must be equal. That guarantees that there's always a solution to this problem and allows us to more easily simulate several steps in time. Obviously, this is not a realistic scenario. Typically, never the inventory is equal to the demand. There's obviously ways to handle this in the optimization problem, but we just decided for the sake of the scientific experiment to leave that aside at the moment. So how did this look like? So we saw the physical network, which is what we have on the left, that represents the warehouses, the customers, and the valid movements between each. And then what we do is we generate an optimization problem by taking the planning horizon, or the number of time steps that we have visibility over, and we basically duplicate this network for each point in time. So it's like having the time dimension become a physical dimension. What do I mean by this? So let's take it apart. So there will be arcs connecting warehouses with nodes of the same warehouse at each point in time. And so an arc between two nodes of the same warehouse represents storing inventory. It means the inventory is moving over in time, but it's staying on the same physical location. For movements from a warehouse to another, like this one here, that would be transporting inventory. It takes time, and it also moves the inventory from one location to the other. And then we have from warehouse to customer arcs, which will be delivering the orders. So in this example of shipping point assignment, we have orders that have already been fixed, or we already have a plan for when to serve them. For example, this one from warehouse 3 to customer 2 is already fixed to be served. And then on the later part of the optimization, we have some decisions to make. Here you see that there are multiple arcs from warehouse to a customer, and we need to decide on which of these will affect the system in the way that the cost will be minimal. So this is our decision space for a reinforcement learning agent. And once the reinforcement learning agent decides on an action here, we can remove the other arcs. So we're kind of simplifying the problem, and we can use linear programming to evaluate what the cost of that decision was. So why even use machine learning for these kinds of problems? Well, as I mentioned, the shipping point assignment is a variation of an NP-hard problem that you could solve with a branch and bound optimizer, or even with some greedy heuristics. The thing with the branch and bound approach is that it scales really, really badly. Here I refer to different settings by their relative size, but when I say a huge setting, it's really nowhere near a real live supply chain scenario. So it very quickly becomes infeasible, and in practice, you couldn't solve the whole supply chain with a branch and bound approach. Then there's a whole area called multi-stage stochastic programming, and the methods there try to optimize a mathematical program, but also take into account randomness and decisions over time. But most of the techniques in the literature, as we found, are very hard to scale, because obviously it would be exactly as doing a branch and bound problem, but adding more and more constraints with each time step that you're considering into the future. So it really is a very complex problem to solve. And finally, one of our motivations is that there have been several papers in the last around 6-7 years that have found very significant advances on combinatorial optimization problems, which is something that was actually a hard thing to do for machine learning algorithms. They're basically just traditional optimization approaches have always been better, but on recent years that has changed with incorporation of reinforcement learning and graph neural network techniques. They've been able to improve the state-of-the-art in problems like the traveling salesman problem, if anyone's familiar with those, maximal click, minimum vertex cut, those kinds of graph problems also have benefited. Here on the right, for example, you can see one of the approaches that they've used on these papers. They encode the optimization problem as a graph of constraints to variables. So that's one of the very interesting approaches. But in general, yeah, we have reason to believe that if this works for combinatorial optimization, maybe we could also make it work for the stochastic case. And then the motivation for graph convolutional networks, for people who are not familiar with a graph convolutional network, they are, you could think of the intuition as a convolution in the image. If you think as an image like a graph of pixels, a pixel is related to all of its neighboring pixels, and then a convolution is just sharing information between a pixel and its neighbors to perform the convolution. In the same way, convolution in a graph would be the interaction of the information of a node with the information of its neighbors. So it's typically like a linear layer where it aggregates node features with neighbor features and then some kind of nonlinearity. And yeah, so it's very clear to see that this kind of network has a lot of valuable information that traditional machine learning methods would not encode. And so we wanted to see if graph neural networks could help us get better results. So to solve this problem, we first need to set up the Markovian decision process. And that requires defining the environment, the reward function, state variables, and actions. So first of all, the actions is choosing the warehouse that is going to be assigned to ship an order. We already talked about that. And then the state is composed by the orders that are currently visible, the inventory for all the products and warehouses, and then the physical network. The environment is composed of several parts. There's the time expanded network generator that it takes the physical network and expands it over time, as we saw before. There's the demand generators, and then there is the physical network that defines what dynamics are valid. And so this environment simulates what happens every time that the agent takes an action, affects the results of the optimization, and it outputs a reward function that is based on some processing of the overall cost of the network and feeds that back into the agent for learning. So one thing that was very challenging about this problem was defining the reward function. It turns out that the results are very sensitive to the function that you choose. We originally were just going to do something like the negative value of the cost of the linear programming that I was mentioning. Turns out that that is not a very good approach, and it works very similarly to a random choice. So we explored a little bit, tried several reward functions. By the way, this graph here, what I'm showing is interplants. As I mentioned before, interplants are movements between warehouses, and you can think of it in this case as a proxy for cost. The reason that I'm not showing cost directly here is because there are other factors like illegal movements that affect the scale. So this one is a little bit easier to interpret, but for all intents and purposes, think of this as cost. And so you can see here that there are several reward function designs that basically work like a random choice. So we really spent a lot of time and found that this logarithmic transformation of cost and illegal movements, or big M movements that they're called technically, was the one that worked best. The takeaway here is, if you're working on a reinforcement learning problem, really take a lot of time for designing your reward function. And then the general architecture of the reinforcement learning agents. So we have all these different components that I mentioned: the physical network, the time expanded, the demands, and the inventories. And we want to aggregate that in some way so that we can create a value function approximation. And what that means is that we're going to approximate what the value of being in a specific state is. And based on that, evaluate what the impact on the value for the states that you would go to if you took a particular action would be. And that is called the Q value of being in a state and taking an action. And so for those not familiar with reinforcement learning, this is the update rule for the Q learning algorithm. And what it's saying is, okay, well, what is the cost of being in this state plus the change in my value based on the reward that I got and the best action that I can take at the moment. I see there are some questions in the chat. Oh, okay, so we'll have a Q&A in the end. All right. Okay, and so for the reinforcement learning part, I decided to create two different agents. One is the MLP-based, and the other one is GNN-based. So the MLP is just a regular multi-layer perceptron with a couple of layers. I am using something called noisy linear, which is just the same as a linear layer, but with some Gaussian noise added for robustness during training. And then the last layer, with no activation, it will give you a vector of the number of warehouses, and that will give you like the value of deciding whether this order should go into that warehouse. And then the features are just a description of the order that you have at the moment. One is how much is demanded of each product. So a dimension of K commodities. There's an indicator of whether the features are actually this here. Apologies for that. There's two sets of features for the MLP, and ignore the rest for now. One is whether a warehouse is valid for a given order. And then the inventory consumption vector will tell you what the inventory would look like if you chose that warehouse for shipping that order. So going back to this, we create a vector for that particular order, pass it through the MLP, and we get the Q values. On the other hand, the GCN agent has a couple of GCN layers, then a graph pooling operation that reduces the dimensionality, and finally a linear layer that does the same thing as before. So what we're doing essentially is taking the physical network, aggregating it, communicating information between the nodes, and then generating a Q value again. And the features in this case are going to be node specific. So there's the supplier demand, depending on if it's a warehouse or a customer, an indicator for the kind of node that it is, and then a one if the node that I'm processing contains the next order that needs an optimization. And then finally, we have a couple of benchmark agents to compare the reinforcement learning. One is a look ahead that just checks, that does a linear optimization for each of the possible decisions of the current order and chooses the best one. So it ignores the randomness completely and just focuses on what it has in front of it. And then the branch and bound that does the same, but considers all possible combinations of shipping point assignments. You can see that this is something that scales really badly because of the number of decisions that arise with each new order and each new sets of warehouses. So the experiment suite is basically, as I mentioned, increasing sizes of the number of warehouses, customers, commodities. This here is the number of orders per day, and then the number of valid warehouses per customer. And this number here is just a reference of how the number of decisions is increasing exponentially. So by this point, we expected the deterministic optimizers to struggle a lot with time. And the hope is that the reinforcement learning agents will be able to optimize much better in the long term. But as it turns out, the results were not exactly as we expected. With each increase in the size, we saw that the performance of the reinforcement learning agents kind of degraded. So on the first one, they didn't do so bad. They were slightly better than a random action, and they didn't get to the performance of the deterministic optimizers, which are these two first ones. And then there's also this greedy heuristic here that we also put in for reference that actually performed quite well. And so you can see as we move on to the medium that the gap between the deterministic optimizers and GNN and MLP is even larger. The random choice is actually even better than the MLP in this case, unfortunately. And this trend continues. When we get to the large environment, we have an even larger gap. The greedy heuristics are still performing quite well, but also notice on this box plot on the right that the time is increasing already quite a bit, and the branch and bound is orders of magnitude slower than all of the other methods, which for these small examples is okay, but if you try to scale this method for production scenarios, it's just not going to work. And then finally, when we get to the last one, the difference in time is huge. And then the difference in performance is also quite significant, with the reinforcement learning agents being left completely behind. So obviously, this was not the result that we were expecting. And so we had some questions about why are reinforcement learning agents struggling to learn so much in these kinds of environments, and why with scale they're getting even worse. One thing that we noticed is that even though the reward function choice that we used worked well for some environments, in general, it seems like up until some point, they were actually very small changes in scale. So even though the box plots for cost show a significant difference between the agents, if you transform this to the reward function values, they're actually almost the same. So it's very difficult, our conclusion was, to make decisions on the very small scale of optimization that is required. Another thing that we noticed, so we tried to remove some variables from the equation and see what happens if we made the inventory assignment at each time step deterministic. And it turns out that removing that source of randomness actually made the RL agents perform like much better, orders of magnitude better than the random choice, very comparable to the deterministic optimizers that are doing the exhaustive search. And so what we concluded from this is that maybe the reinforcement learning agents are trying to learn too many things at the same time. So that actually opens up a lot of future work scenarios that we're interested in working perhaps in a future paper. And the most exciting avenue is using something called differentiable convex optimization layers. And the idea is that you take this mathematical optimization problem that has random variables encoded to it, you define it with this kind of DSL, and then you encode this information into a neural network layer. So essentially what you're doing is you're giving the value function approximation, the GNN or the MLP, you're giving it information about the actual optimization problem. So it doesn't have to learn about that. It can focus on learning just about the decisions and just about the cost of taking certain actions, but you already have that prior information into the layers that is going to make learning much faster. And as we know, learning and reinforcement learning is a little bit more inefficient than in other kinds, like in supervised learning. So I believe this is something that could really improve the results significantly. Another thing that we would like to try, and this last bullet point, is adding surplus inventory. As I mentioned, it's something that we did to relax the problem and make it easier to optimize. But it also turns out that it gives you less room for optimizing. So if you wanted to save inventory to make better decisions in the future, at the moment it's very difficult to do that because you have very tight inventory margins. And it's both not realistic and not helpful for the long-term optimization that we're trying to do. So in conclusion, we talked about the shipping point assignment. It's a novel stochastic optimization problem that's very challenging. We saw some experiments that showed that our deep QN or deep reinforcement learning agents weren't able to perform even similarly to deterministic optimizers, not even using GNNs. So we rejected our original hypothesis. However, we learned that there's likely some causes to this result, that the randomness of inventory and order simultaneously, as well as having to learn the optimization problem alongside the variables, might be hurting those agents. And then we saw some of the future avenues that could be pursued in this problem. I personally have a lot of faith in this new approach with the differentiable layers, differentiable convex optimization layers, and we'd have to see what happens there. Thank you very much for attending this talk. Here's some of my contact information. Thank you so much to Gautier for making this possible, and also Luis, who has helped me a lot during this thesis work. His advisory was exceptional. Oh, and by the way, I do have a couple of slides here that I just wanted to like quickly show about some of the more technical things that were part of this work. Some of the libraries that I used: Pytorch Geometric, which extends regular Pytorch and allows you to make this graph convolutions and these kinds of operations. It's very elegant, and I encourage you to check it out. There's also Pytorch Lightning, which helps a lot with all of the boilerplate code of training. You define a minimal set of things about your network, the training step, the forward, basically, and then the optimizers, and it gives you a lot of benefits for it, that you don't have to worry about setting the devices, GPU. If you want to do quantization, stuff like that, it's a very cool library. Then there's OpenAl Gym, which is what I use to define the reinforcement learning environment. And Google OR Tools, which is used for the mathematical optimization problems. It has network flows, which is the graph transportation problem that I showed. And then also for integer and linear programs, that's also what I'm using. And then weights and biases for all of the for all the training and experimentation. It's also a very nice library to check out. And yeah, I think that's all I had. I think we're ready for some questions.